Welcome to lecture number 9 of VLSI design KEC 072. We are going to continue from our previous lecture. In the last lecture, we have discussed about linear delay model, which introduced us to the concept of logical effort, fan out and parasitic delay. Now, we want to extend that concept to different paths which might exist in a circuit. Okay. So, how do we calculate the logical effort in different paths in different stages, and also discuss something which is known as downscaling of VLSI circuits. Okay. So, a circuit VLSI circuit is not very simple, it is not very straightforward in terms of its topology, in terms of complexity. The signal which starts from the input and reaches the output may not do so in a straight line or in a very straightforward manner. There are different topologies of circuits available. There are different paths, different stages which might exist in between before the signal which starts from the input end reaches the output end. Okay. So, from the designer's point of view, one might need to choose the fastest circuit topology with lowest delay and optimized gate sizes for the given logic function, so that you can estimate and minimize how much delay or propagation delay is being propagated from the input to the output. Okay. So, the linear delay model, as discussed earlier, it allows a VLSI designer to quickly estimate what is the best possible number of stages and what is the best possible path which might be available, such that the delay for the given application can be minimized. Okay. So, take this example. This is a typical you can say a path which is existing starting from an inverter moving towards a stages of logic gates, again an inverter is there and then the signal reaches the load. Okay. So, this number 10 here is that 10 inverters are driving X input NOR gate, which is further driving a Y input NAND gate, which is driving a Z number of input of inverter. Okay. So, this is a multi-stage path, this is a typical multi-stage path. The blue dashed arrow is a chosen path or is the selected path, okay, because if you have x number of inputs say at NOR gate, there are x number of possibilities how the signal can propagate, and same applies to the NAND gate, to the further inverter and all that. Okay. So, the path of interest highlighted here, it shows that logical effort G, okay, is actually size independent, okay, while the electrical effort, which is a representation of the fan out. Okay. So, if you remember the equation for normalized delay G dot H plus P, G is your logical effort, okay, and H represents your electrical effort. Okay. So, size does not affect logical effort. For inverter G is 1, for a NAND gate it is n plus 2 by 3, okay, and for a NOR gate it is 2 n plus 1 by 3. Right. So, you can see that for this 2 input NOR gate your logical effort is 5 by 3, for this NAND gate it is 4 by 3. Okay. So, we are talking about two input logic gates here. Okay. For inverters logical effort is equal to 1. The fan out, which is ratio of output to input capacitance, if this input is driving this NOR gate with output capacitance x, the electrical effort is x over 10, where 10 is the capacitance of this initial inverter here. Okay. Similarly, at this stage the fan out or electrical effort is y over x, here it is z over y, and here the load capacitance is 20 units, the input capacitance of this inverter is z. So, your electrical effort becomes 20 over z. Okay. So, logical effort is a measure of complexity, electrical effort is a measure of fan out. Right. For a particular path with multiple stages, the total logical effort denoted by an uppercase G, okay, till now we have used smaller case for logical effort, but when you are talking about multi-stage path, okay, the the net path logical effort is basically a product of each stage, logical effort of each stage. Okay. So, in the previous example, if we had these stages 1, 2, 3 and 4, if I multiply the logical effort of each stage, I will get the total path logical effort. Similarly, the path electrical effort H can be given as the ratio of the output capacitance of the path divided by the input capacitance, which is presented by that path. Okay. So, we are only interested in the path which the signal is taking. We take the output capacitance of the load and divide it by the capacitance where the signal originated, the input capacitance. Okay. So, that gives us the path electrical effort. Okay. Now, we have seen that the path effort generally denoted by a lower case f is a product of G dot H. Okay. So, logical effort and electrical effort multiplied, that gives you the path effort or stage effort. Okay. For this kind of circuit, multi-stage circuit, we basically take all the products of each stage, logical effort of each stage, okay, and electrical effort of each stage, multiply it and keep multiplying for all stages, and the net value which you get is the path effort. Okay. So, the effort for the entire path. Now, this is till now it is very straightforward that you have a multi-stage network. Okay. Every stage is going to have a logical effort, every stage is going to have an electrical effort. You multiply those two for each stage and the final product is going to give you the path effort. Okay. And then you can do the same for the parasitic delay of the path and then add these to the product and the parasitic delay, and you will get the normalized delay for the path. Okay. But signal movement may not be that straightforward, there can be branching also. Okay. A signal, say if you look at the circuit which is given in this slide, you have an inverter here, input capacitance of 5 units, driving an arrangement where you have this inverter of input capacitance 15 unit, another inverter input capacitance of 15 units, driving a load output capacitance 90 units and output capacitance 90 units. Okay. If I want to get the logical effort or the stage effort of this path, okay, say I have chosen a particular path highlighted in this blue. Okay. So, the blue dashed line basically shows the selected path. Okay. If I want to calculate the path logical effort, now we are talking about inverters only. Okay. So, this inverter has logical effort 1, this inverter has logical effort 1. Okay. So, the product of these two stages, the total path logical effort is going to be 1 also. Okay. The path electrical effort ratio of output capacitance, which is 90 to that of input capacitance. Okay. So, we have shown that the path logical effort is product of logical effort of each stage, and the path electrical effort is ratio of the output capacitance to that input capacitance in the chosen path. And then the stage, the effort, the path effort is simply the product of each stage. Okay. Going by this explanation, I am going to have the path logical effort as 1 and the path electrical effort as 18. So, the effort delay or stage effort is simply going to be 1 times 18, which is 18. Okay. But if I try to analyze it in more detail, I want to analyze this circuit in more detail. If I say that the stage effort, instead of writing it as G dot H, okay, instead of writing as G dot H, if I write it as G 1 G 2 into H 1 H 2. Okay. So, G 1 is for stage 1 logical effort of stage 1, G 2 is logical effort of stage 2, H 1 is electrical effort of stage 1, H 2 is electrical effort of stage 2. Okay. So, this G 1 here, this stage here. Okay. So, I have an inverter, then again also I have an inverter. Okay. So, this remains at 1 times 1 only. Okay. this is G1 dot G2. Okay. What about H1 and H2? Okay. If I see at this stage, this input stage, from the point of view of this input stage, it is seeing a branching here. Okay. So, it is actually driving this and this. So, the total output capacitance it is seeing is 15 plus 15. Okay. So, H1 basically is going to be 15 units from one load, 15 units from next inverter divided by the input capacitance. Okay. Sorry, this is going to be 5, okay, because the input capacitance here is 5. This is going to give me 6 units for H1. Similarly, for H2, I see a load here, okay, 90. If this is my chosen path, my output capacitance is 90, okay, and my input capacitance is 15, right. Now, I am talking about this stage here, right. This is my second stage. Okay. So, this is my second stage, this was my first stage. Okay. Now, if I multiply, I am going to get a path effort equal to, this is already 1, G1 and G2 being inverter logical effort is 1. So, 1 times 1 is 1 only. H1, H2 is 6 each. So, I am going to get 36. Now, this is twice the number which I got in the previous slide. Okay. So, there is something difference here. The difference here is this point here, which is nothing but branching. Okay. So, for these kind of networks where you have multiple stages, multiple paths and branching as well, you have to introduce another term which is known as branching effort. Okay. And this is the ratio of the total capacitance seen by a stage to the capacitance on the chosen path. Okay. So, in the previous circuit, if this was my chosen path, okay, so that will be the capacitance of that path, and the numerator will have the capacitance of that path plus the path which I did not take. Okay. So, in this given example, right, I am going to have this capacitance here 15, this capacitance here which is 15. Okay. So, this is the path I took, this is the path I did not take. So, this is C on, this is C off. Okay. So, I will add these two, right. So, B in this case is going to be 15 plus 15 divided by the capacitance of the path I took, C on path. Okay. So, this in this case you only have two options. Okay. You have only two paths, this is your path 1, this is your path 2, this path I took. So, this had a capacitance of 15 unit, this is the path I avoided. So, this also has a capacitance of 15 unit, that has to be included. Why? Because this driving input is seeing both the capacitances, even though you are taking this as the chosen path, the driver here is seeing both of them. Okay. So, you take the capacitance of both the stages into account. Okay. This is going to give you 2, a branching factor of 2. If you multiply this factor to the stage effort here, you are going to get the total stage effort as 36, which is the value you got here. Okay. So, we introduce what is known as branching effort, mathematically described as the ratio of capacitance seen by a stage to total capacitance divided by the capacitance of the path which was selected. Okay. And the net path branching effort is the product of the branching effort between stages. Okay. So, in this example we had only 2 stages. So, you had only 2 choices, right. So, net this capital B, uppercase B was equal to 2. If you have multiple stages, you are going to have different branching stages for each stage. Okay. So, you take the branching effort of each stage, multiply them together and you are going to get the path branching effort. Okay. When you are talking about single stages, we generally use lowercase notation, and when you are talking about the path or multi-stage path with branches, you use the notation of uppercase. Okay. So, by taking all these path efforts into account, you finally get the total value of path effort, which is the product of logical effort of path, branching effort of path and the electrical effort of the path. Okay. Multiply all three of them together and get the path effort. The total path delay in this case now becomes the summation of individual normalized delays, right, where this product here, this is this product here, plus the parasitic delay of the path. Okay. When they are added, so this is an extension of the linear delay model for a multi-stage multi-path network with branches. Right. The path effort delay and the path parasitic delay used in this expression, okay, for the total normalized delay, this is the summation of f. F is the path effort of each stage. Okay. So, this is the path effort of each stage, and this is the parasitic delay of each stage. Okay. Right. And then when you summate them, you add them together, you are going to get the total delay, which was our initial aim. Right. The path delay is minimized. Okay. So, this is a very important result, that the path delay is minimized when each stage bears the same effort. If a path has n stages and each bears the same effort, that effort is written as again product of individual logical and electrical efforts equal to the path effort to the power 1 by n, where n is the number of stages which you have in the path. Thus, if you want to minimize this expression, okay, so d equal to n f 1 by n plus p, this is your linear delay model. This is the extension of your linear delay model, right. This is a very important result, because if you see, the number of stages is basically having an impact on your overall delay. Okay. So, the minimum possible delay, this is the minimum possible delay basically, okay, and this is going to be obtained when each stage bears the same effort. The effort we are talking about is the stage effort f, which includes two things, the logical effort g and the electrical effort h, and g is basically a measure of complexity and h is a measure of fan out. Okay. So, how complex the gate is? Complex here means how many transistors are required to produce that logic gate, okay, and fan out here means how much is the output capacitance of the load being driven and how much is the input capacitance of the gate driver. Okay. So, these things, when multiple stages are bearing the same amount of effort, you are going to minimize your overall normalized delay. Okay. So, this was all about logical effort of path. Okay. I hope the concept has been clear to you. The linear delay model comparing with the RC delay model is more simpler, because it uses a simple algebraic equation. If you remember, before RC delay model, we did what was known as transient response, which involved solution of differential equations, which was even more complicated. So, with each model we have tried to simplify how delay is estimated, how delay is quantified. Okay. Linear delay model is considered quite simple, because it is a simple analogous to the equation of a straight line, where you have things like logical effort, electrical effort, parasitic delay. The logical and electrical efforts are multiplied, added to the parasitic delay, and that produces your normalized delay. You can calculate for individual stages. If the path has multiple stages, multiply them together to get the overall path delay. If there is branching in any path, you use the branching effort also, which produces an extra factor, okay, and that takes into account if a particular path is branching also, right. So, that is all about the linear delay model and logical effort of path. Okay. We move to our next topic, which is known as scaling. Okay. I am sure you have heard and read about scaling. If you are into this field, if you have any familiarity with the field of microelectronics, scaling has been a very common trend. Okay. Circuits VLSI circuits consisting of lot of transistors. They have been downscaled over the years. The critical dimensions, the width between different transistors, the width, the length of the channel, the width of the gate, the voltages, the doping, all have been scaled down or up in such a way that you can put more and more transistor on a per square millimeter area of silicon. When you put more transistor on a single silicon substrate, you increase the functionality. Okay. So, the area of silicon chip reduces at every technological node. Okay. The common nodes being 180 nanometer, 90 nanometer, 45, 22, 13, 7. Okay. So, these are in terms of nanometers. We hear about these technological nodes, which is basically a downscaling node. Okay. So, historically in past many decades we have seen a 30% improvement in circuit density every 2 to 3 years. This is the quite famous Moore's law. Okay. Constant downscaling, as I have said, of transistor dimension results in performance improvement such as faster switching, okay, which is important for digital applications. You have to switch from 1 to 0 and 0 to 1 at a very rapid rate. Okay. Reduced power consumption, this is a very broad field of low power VLSI design, where you have to produce portable electronic devices which consume very less power, and economical manufacturing. Obviously, when functionality increases, the revenue increases, and that can be sent back to the manufacturing cycle also. Okay. So, scaling can also result in fabrication challenges, noise and reliability issues. Okay. So, you have to take care of all things like related to the performance of the chip before you go for final production. Okay. So, scaling of the Mosfet or metal oxide semiconductor field effect transistor is generally categorized into 3 types: constant voltage scaling, constant field scaling, and lateral scaling. Okay. And there is a common model known as Dennard model, which is used for scaling the first order constant field MOS technology. Okay. And scaling of the transistor involves scaling of critical metal oxide semiconductor by a factor commonly known as S, while maintaining or keeping the other characteristics of the MOS device constant. Okay. So, either you can only do the physical dimensional scaling in all 3 dimensions x, y and z, or you can scale down the voltage level of the device, or you can scale the doping concentration densities, or you can do all these 3 together. Okay. So, these are some of the approaches which can be used for scaling down the way scaling is implemented. Okay. For those transistor where the feature size was below 1 micron, constant voltage scaling was quite common. Okay. Constant field scaling comes slightly after that, when the feature size reduces further. Here, in addition to the voltages, you have physical parameters like the width, channel length, oxide thickness, supplied voltage. They are all factored. They are all scaled down by a factor of 1 by S. Okay. So, they are all downscaled. Lateral scaling, on the other hand, is a very localized form of scaling, where only the gate length is scaled, while all other dimensions, voltages and doping concentration remain same. Okay. This is commonly known as gate shrink. This has limited applications, this has limited possibilities, because if you scale down one parameter and keep others constant, it produces fabrication challenges. Okay. The table which is shown on the slide basically shows how much of the impact scaling has on different parameters. Okay. The column, the leftmost column, has some major parameters like channel width, length, doping in the substrate, oxide thickness. This is your gate oxide thickness or dielectric thickness, the supply voltage, threshold voltage, saturation current, effective resistance, gate capacitance, gate delay, clock frequency, power dissipation, area of the chip, power and current densities. Okay. And the symbols are also given, and for the 3 scaling techniques, constant field, constant voltage and lateral scaling, you can see how the scaling happens of different parameters. S being a number higher than 1, obviously that only then you can say that the scaling is downscaling. Okay. So, for constant field, you can see almost every parameter except your effective resistance is getting scaled, okay, either downscaled or upscaled. Okay. The doping and the clock frequency and current density, they are being upscaled while all other parameters are downscaled. Constant voltage scaling on the other hand, your voltages, supply and threshold voltages are not scaled, your power density in that case is not scaled, and while all other parameters are being scaled. Lateral on the other hand keeps majority or keeps more parameters constant, it does not scale them. Okay. And what is being scaled is mainly the length, okay, and that affects that has a secondary effect on other parameters. Okay. So, you only scale in lateral scaling, you only scale the gate the channel length or the gate length, and all other electrical or non electrical parameters tend to scale up or down scale with it. Okay. So, this is the impact which scaling has had on the feature size. The vertical axis shows the feature size in microns, and with years, okay, you can see how the feature size has constantly reduced. This basically means that you can pack more and more transistor on the same amount of silicon area, which produces higher functionality, better switching, lower power consumption, more functions are available to the end user at reduced prices, okay, and that basically is a cycle which keeps going on and on with respect to scaling. Okay. So, with that we come to the end of today's lecture. We have explained about logical effort of path, okay, which is a numerical way of estimating delay in a multi-path multi-stage VLSI circuit, and we have also discussed the concept of scaling, which allows us to reduce the size of the Mosfet, so that you can put more and more devices for a better circuit. Okay. Thank you.